Hi, this is Professor Robert Beverly, and this is CS 4538. Today, we're going to talk about Bluetooth in mobile device and wireless security. So Bluetooth. Bluetooth is an old technology. Bluetooth was invented by Ericsson in 1994 as a wireless replacement for RS-232, where RS-232 was the prevailing serial standard for interconnecting peripherals at the time. The word Bluetooth actually comes from the Danish king who was able to actually bring all of the Danish tribes together in the 10th century. His name was Harold Bluetooth. That's the bit of trivia for today. The idea here is that Ericsson, also a Scandinavian company, was going to bring together all of the different devices that were prevalent and expected to come online in one sort of ubiquitous protocol. Bluetooth, of course, has been around for a while and has been standardized by the IEEE, most particularly in 802.15.1. As you all know, Bluetooth is ubiquitous. It's everywhere. The stats I've found said that there were 3 billion devices that included Bluetooth shipped in 2014, and that there's an estimate of more than 10 billion devices that will be installed and in production by 2018. So Bluetooth provides what we call a WPAN, or a wireless personal area network. It's important to note that Bluetooth is an ad hoc, single-hop wireless protocol. This is in contrast to many of the other protocols we've seen recently, like GSM or like Wi-Fi, both of which are single-hop but actually have infrastructure. When we talk about ad hoc, we mean that two devices that have Bluetooth capability can communicate without the help of a base station or any other infrastructure. So some examples of Bluetooth you're all familiar with. Mobile phones support Bluetooth, the headsets that they use. Headphones these days support Bluetooth. Of course, keyboards, mice, smartwatches. My personal favorite, the OBD2 dongle that I use on my car to wirelessly get diagnostics off of the onboard diagnostic port, and I'm sure there's many others. So let's talk about some of the security with Bluetooth. One of the main mechanisms for providing security is the pairing procedure. And most of us have probably done this before. The idea of pairing is really to enable access control, i.e. which devices can connect to which other devices. The security model for pairing is that security is implemented via a PIN, or a personal identification number. Once the PIN is entered correctly, both sides will then establish what's known as a symmetric link key. This requires user interaction typically. Usually the user has to enter the PIN. However, there are some devices that don't have keyboards. Some of these devices may have a hard-coded PIN, in which case one of the security models is to put the device into what's known as an undiscoverable mode, such that it will only pair once it's in this discoverable mode. We'll talk more about this undiscoverable mode as we go along in the lecture, as it's now quite prevalent as a security measure. The idea being is that different devices will hide their presence and won't advertise so that they can't be scanned for or discovered. So with pairing, each device must enter a 16-byte PIN. This is a UTF-8 PIN. But in practice, is there really that much complexity in PIN implementations? And the answer, perhaps unsurprisingly, is no. There's relatively low entropy in popular PIN implementations. Most pins are short. Typically, they're 4 digits or 4 bytes. Most pins are numeric only. So 000 or 01234, and many pins are fixed, as we said before, by the manufacturer, perhaps because there's no way to input a different pin on the screen. And many of these pins are fixed to well-known values, like all zeros or 1234, things like this. So let's talk about some of the crypto that's actually used behind the scenes to implement access control, to provide confidentiality, etc., etc. So the suite of protocols that are used is known as SAFR+. So SAFR is an acronym for the Secure and Fast Encryption Routine. This is a public, unpatented algorithm suite that was one of the candidates for AES. It was rejected, but got picked up by Bluetooth. Was rejected, sorry, for AES, but got picked up by Bluetooth. It includes 3 block ciphers that we'll look at today. There's the E22, the E21, and the E1 block cipher. In addition, for privacy and encryption, Bluetooth uses something known as the E0 stream cipher, which again is public. It was new and designed exclusively for Bluetooth. So when we talk about the security of Bluetooth, we're going to focus on 3 steps: the initialization key, the link key, and the authentication. So let's talk about the initialization key, or K_init. Kinit is created from the E22 block cipher using inputs of the Bluetooth address, the PIN, and the initialization random value. Here, BD adder is the MAC address of the slave, the PIN is the shared secret we just discussed, and INRAND is a random 128 bits sent by the master. We'll talk about master and slave in a bit later when we talk about the MAC protocol, but think of the master as one end of the connection and the slave as the other. Here we see an illustration of the generation of the Kinit key. Here the master is on the left, the slave is on the right. We call the master A and the slave B, and in the middle here we see the messages going across. The master has generated the random 128-bit INRAND, has sent it across. At this point, both sides will take the BD adder, the INRAND, and the PIN, run it through E22, and generate that Kinit. Once we have the Kinit, the next part of the process is to generate what's known as the link key, or the K_AB. To generate this key, both the master and the slave generate 128 random bits. So we call these the LK_RAND A and the LK_RAND B, which means the link rand from A and the link rand from B. You can somewhat think of these as the S-nonce that we saw before when we were looking at some of the Wi-Fi protocols. Here, what happens is instead of these being sent over directly and in the clear, they're actually XOR'd with the Kinit key. So each side takes their random value, XORs it with Kinit, and sends it over. This works just fine because since each side also has the Kinit, they can simply perform the XOR to recover the link rand that was sent to them. Then each side generates the link key A or the link KB. This is generated using the E21 block cipher, and it takes as input the Bluetooth address of A, the link rand of A. Similarly, the link key for B takes the Bluetooth address of B and the link rand of B. Finally, we get to generating this link key, this shared link key, K_AB, which is nothing more than the XOR of the 2 individual link keys. We can see this graphically here, perhaps much easier to see. On the left, we've got the master that has generated the link rand A. Similarly, the slave has generated link rand B. These are sent over, but only after first XORing them with the Kinit. But that's fine because when they're received, it can simply XOR it with Kinit to recover the other side's link rand value. Then both sides use the E21 algorithm to compute the link key for KA and the link key for KB, and those are XORed together so that each side then has the KAB, or the overall link key. Finally, mutual authentication occurs. This is one of our standard challenge response type protocols, where there's a random value, an authentication random challenge that's sent over, and then there's an SRES, or one of these signed responses. This will look very similar to what we saw in the authentication procedure for GSM. Here we use the E1 block cipher, and it computes the SRES as a function of E1, that link key, shared link key, KAB, the random challenge, and the Bluetooth address of the other side. If successful, of course, we have mutual authentication, so the exact reverse is done. Here we see this graphically where we have the verifier, or the side A, and the claimant, the side B. So here the idea is that A is verifying it is doing the authentication of B, and then we'll reverse the verifier and claimant roles when we do the other side of the mutual authentication. So the verifier sends over its random challenge. The claimant at this point will then use that KAB key, the Bluetooth address, and the challenge to generate the signed response and send that over. Of course, the verifier can check that signed response, and if it is in fact correct, they'll switch roles to do the mutual authentication. So this is the list of messages that Eve observes through this whole process of when two devices pair. There's the initialization random that's sent over during the process of generating the init key. There's the link rand A. Of course, that is XOR'd with the K init. There's the link rand B, which is XOR'd. We see the authentication ran for A, the signed response, and the authentication ran for B and the signed response. The astute observer will note that this provides us with our classic known plaintext attack, or KPA. Here, Eve, the observer in the middle, observes both the challenge and the response, or in essence, she observes the bit of plaintext and then the corresponding ciphertext after it's been encrypted with the E1 block cipher. And again, we'll turn to some of our standard techniques. One of the standard techniques that we've seen that's remarkably effective is simply brute forcing. So what would be a brute force in this particular realm? The idea is we'll have to guess the pin because we don't know what it is. So we'll guess a pin. We'll then generate a candidate KInit value from that pin. From that, we'll generate the candidate KAB link key, and then we'll use KAB to run through the block cipher E1 along with this challenge to see if the signed result we get out is in fact the value of the signed response that we were expecting. And we iterate until we find the correct pin. Here's a graphical depiction of this with a flowchart. So we start at pin 0. We compute a candidate KInit value, which we can do. We decode both the LK-RAND and the LK-RAND-B by XORing. This allows us to then calculate a hypothesis for the KAB link key. And from that, we can calculate a candidate signed response from the challenge. We check to see if the signed response matches the actual signed response that we observed. If it doesn't, then we simply go to the next pin. So we try pin 1, pin 2, pin 3, so on and so forth. If it does, we'll check the other side of the mutual authentication. If that works as well, it turns out that the pin we guessed is correct, and we have now cracked the pin for Bluetooth. Simple, right? So this was first shown in a MobySys 2005 paper, so about 10 years ago, from Shaked and Wool. At the time, they used a Pentium 3 and a Pentium 4. What we're looking at here is a plot of the amount of time it took to crack a pin. Here we see on the x-axis the number of pin digits, and on the y-axis time in seconds. Note that this is logarithmic. And in the paper, which we haven't discussed or distributed, but it's good to know, what happens is they compare different versions of their particular cracking, brute force cracking implementation. There's the as-is version, which is just a untuned version. There's a basic version which uses some compiler flags, and then there's some other versions that use various speed-ups and tricks such as lookup tables to give some speed improvements. The key point here is that this plot was generated using a Pentium 3, which was, reasonable technology at the time. Even with the Pentium 3 with 4 digits of pin and their best implementation, you're looking at under a second to crack. With 7 digits of PIN, we're looking at 269 seconds to crack. So here we're talking about a particular attack that is almost in real time. This is less than 5 minutes. They also found that there was a 10 times speed up simply going to a Pentium 4. So here we can consider the ability to crack pins as essentially trivial. Now note that it's not always quite this easy. Devices try to store this link key, this KAB. So remember, KAB happened after we input the pins and we generated the Kinit and so on and so forth, right? But once we've paired the devices, they don't remember the pin. What they remember is this KAB. This allows the devices to store the link key and then proceed directly to the authentication phase. This prevents the known plaintext attack that we discussed earlier. It turns out that this isn't that severe of a problem. There's several ways to perform what's known as a repairing attack. And if you're curious, you can see this MobiSys paper from 2005 for some of the details. The high-level idea is that it's very similar to what we did when we studied 802.11, where we would spoof different kinds of frames. For instance, the disassociation frame. Here, one of the ideas is we can spoof a particular kind of Bluetooth control message that basically says the claimant has no link key. And this will force many of the devices to simply do a repairing. When the devices do repair, this will reveal those known plaintext attack messages, both the challenge and the corresponding encryption of the challenge, allowing us to perform our PIN attack. So what are the implications here? One of the big implications is that the only security in Bluetooth comes from the physical layer, and we're going to talk about that next. At the time when that paper on pin cracking was published in 2005, there was no actual real-world implementation, and this was due to the simple difficulty in eavesdropping. The paper that we have for today, called Bluesniff by Spill and Bitteau from 2007, actually brings together this final piece. To understand how Bluesniff works, we need to know more about the actual operation of the Bluetooth radio, its PHY, and the MAC. So Bluetooth Class 2 devices have a range of about 10 meters, and for our purposes, we'll talk about a data rate of about a megabit per second. So this is the classic version 1.2. There's a bunch of different versions of Bluetooth, but for our discussion, this will suffice. The MAC involves both a master and a slave. Time is slotted, where the master will transmit in even slots and the slave or slaves will transmit in odd slots. The master chooses which slaves to address. The physical layer operates in the ISM, or in the Industrial, Scientific, and Medical band. This is the public band that you'll recall also Wi-Fi operated in. This is the 2.4 gigahertz band. The bandwidth here is divided into 79 1 megahertz channels. And what happens in Bluetooth is that it uses frequency hopping spread spectrum. So in Bluetooth, the Bluetooth is changing the channel, the frequency, 1,600 times per second, or once every 625 microseconds. The sequence, the hopping sequence, meaning which actual frequency it's used at a given instant in time, is a function of the master's MAC address and the master's clock. So we're going to talk about that. This presents one particular difficulty to sniffing, because what's happening here is that the radio is changing frequencies once every 625 microseconds, and we don't necessarily know what frequency it's changing to. While we could have 79 radios all listening simultaneously, this presents several practical difficulties. Further, Bluetooth employs something called whitening. The idea of whitening is it's simply a scrambling procedure that improves error resilience and also provides some additional security. The scrambling sequence is a function of the clock as well. we're going to talk about how the whitening works and how to de-whiten the packets. So here's a graphical illustration of what we mean by the frequency hopping. So the master here initiates the connection. Bluetooth is packet-based, and for the version of Bluetooth we're discussing, there's one packet sent in each time slot. On the right here, we see the master and the slave, and every 625 microseconds, there's a dashed line. So these dashed lines that are going across horizontally are demarking the different time slots. And so the idea here is that each frame or packet is sent in one of these time slots. So for instance, what will happen is the master will send a data packet or frame to the slave in a particular time slot of 625 microseconds. And it will do it at a particular frequency that's appropriate for that time slot. In the next time slot, remember that the masters and slaves alternate time slots. The next frequency that's used is a function of whatever the next frequency should be based on the hopping sequence. In this case, the slave sends an ACK back to the master. Then in the next 625 microsecond slot, the master sends its next data frame, again on a different frequency, so on and so forth. So this hopping frequency, just to reiterate, is determined by two things. It's determined by the master's clock and the MAC address. The clock is a global 28-bit counter, and it ticks every 312.5 microseconds, or twice a frame. Let's talk about Bluetooth addresses in the MAC. So in the MAC, we have 6-byte MAC addresses, but here we divide them a little bit differently than we've seen in the past, and there's some interesting artifacts of this. First of all, we have what's called the NAP, or the non-significant address part. This is the most significant 2 bytes. Next, we have something called the UAP, or the upper address part. This is a single byte. And then finally, we have 3 bytes, known as the LAP, or the lower address part. So an interesting design choice in Bluetooth is that only the LAP, or the lower address part, is present in the packet headers. This is very different than, for instance, Wi-Fi, where of course when we looked at packets in Wireshark, Wi-Fi 802.11 packets in Wireshark, we saw the complete 6-byte MAC address. Further, if we look at the rest of the packet header, what we'll see is that there's a header that contains what's known as the access code, or the access pattern. This is 72 bits that contains the 24 bits of LAP, those 3 bytes of the lower address portion, 34 bits of checksum, and 14 bits of error and sync. The remainder of the frame is whitened or scrambled, and that's shown here with this arrow above the frame after the header that says whitened data. So what is whitening exactly? So the idea here is that the whitening sequence is designed to decorrelate the data for better error robustness, as well as increased security. And to do this, it uses a fairly simple linear feedback shift register, as shown in this picture, and it generates a pseudo-random bit stream. This pseudo-random bit stream is simply XORed with the data. That's what we mean by whitening. How is this feedback shift register actually initialized? Well, it's initialized with 6 bits of the clock. It turns out that the whitening procedure is actually fairly straightforward to de-whiten. We'll see that next. Let's talk about sniffing though. How are we going to sniff? So we need 2 things to effectively perform the sniffing. We need the master's MAC address, and we need its clock. Of course, we can do this by establishing a connection. However, this presents another practical difficulty. First of all, we may not be able to establish a connection. The device may be undiscoverable, so we can't inquire without knowing the MAC. And of course, we can't get the MAC without the clock to unwhiten it. So this presents something of a catch-22. Further, we may be simply sniffing in the middle of a conversation and we want to perform a passive type of attack. And we simply can't do this kind of inquiring to figure out the MAC and the clock. And this is where some of the Bluesniff work actually comes in. So let's talk about unwhitening. Their unwhitening procedure is fairly straightforward. The idea is that they're going to listen on only one channel. So they're going to tune their radio to one of these channels. And the point here is that because we're changing the frequency 1600 times per second, even though we're only listening on one channel, we're going to observe a whole bunch of frames. And then, as always, we're going to perform brute force. So if you remember that linear feedback shift register, it was initialized with 6 bits of the clock. We can brute force all 6 bits and come up with 64 possible initial linear feedback shift register states. And of course, we can make a table of the output sequences. So what we can do is simply have a lookup table that has all the possible values that this whitening linear feedback shift register could have taken when it was initialized, and a table of the output sequences. So now what do we do? Well, now what we do is we can simply XOR the output of this linear feedback shift register with each frame and check against the CRC to find which 6 bits are correct. So because the whole packet is whitened, including the CRC, when we run the whitening sequence to de-whiten it, if the CRC checks, this provides us a way to do self-validation. We can know that in fact the particular value we chose was correct for the de-whitening. Fairly simple. Next, let's talk about finding the MAC. Because we can't figure out, again, the hopping sequence without knowing the MAC and the clock. We know that there's 3 bytes that are in the clear, that lower address portion. The problem is that the upper address portion is not in the header. Luckily, the header contains something called a HEC, or a header error code. And it turns out that this is actually calculated from the UAP, or the upper address portion. This is again computed using a linear feedback shift register, and this particular type of linear feedback shift register can be run in reverse, unambiguously. So in the paper, they describe how to actually reverse the header error code to actually output the upper address portion. Finally, there's the non-significant address part. The non-significant address part presents a little bit of a difficulty because it's 2 bytes and there's no way to determine these 2 bytes from the received packets. While the paper claims that 1 byte is typically 00, I have definitely not seen this in practice. However, we can definitely make some educated guesses. The first is, we know that there are certain byte values that are used more often than others. So we can make educated guesses. For instance, the IEEE OUI, or Organizational Unique Identifier, we know that the first 3 bytes are typically assigned to particular manufacturers. And so there's typically 3 bytes of the NAP that we can guess. Further, brute forcing these is not that hard. If we have an educated guess, it's not that hard. Even if we don't, we're talking about 2 bytes. Here, this is 16 bits or 64,000 different tries. At worst, we'll take 64,000 different tries. This will require us to send pings to the candidate MAC. So finally, bringing it all together. Remember that USRP we discussed when we talked about GSM? The USRP is this Universal Software Radio Peripheral, and this is a really neat device that allows us to do what's known as SDR, or Software Defined Radio. The neat thing here is that the authors built in this Bluesniff paper a Bluetooth sniffer from this commodity USRP. The implications are pretty cool here. What this means is that now they can effectively decrypt all of the encrypted communication between two nodes in a Bluetooth network, between a master and a slave. So here we could decrypt the communication between, say, a phone and a headset, or say between a phone and a computer, or between a watch, or between a car. There's some pretty interesting implications here. Finally, I wanted to show you a quick demonstration of doing some sniffing in Kali. So the first thing I'm going to do is I'm going to show you that here I have, there we go, I have this HCI 0. So this is actually the Bluetooth on my laptop that's being passed through to Kali over USB. So here I've got this Bluetooth interface that Kali has access to, and what I can do now is I can actually run what's known as an HCI scan, if I can find that. All right. So I can do an HCI scan, HCI tool with this interface, HCI 0 scan. So if I run that, and this will take a second to run, it's not going to actually find anything. So why is that? I actually have my phone sitting here right next to me. It's running Bluetooth, and it's even associated with some other devices. The reason is that all of these popular devices these days, including my Android device, do not actually advertise their address. So they are running in undiscoverable mode. So I'm going to go to Settings, I'm going to click on Bluetooth, and now it says that my device is visible. So if I run the scan again, hopefully we're going to see my Bluetooth actual device here. And there it is. At this point, I can do things. Remember I said we could run a ping? So here I'm going to do an L2 ping. So I'm actually sending a Bluetooth ping from Kali to my phone that's sitting right next to me. And so this illustrates this whole procedure of performing a ping. So I hope you've learned some neat things about Bluetooth, and we'll cover more of this later. Thanks, and have a great day.